Welcome to this presentation on learning 3D shape proprioception for continuum soft robots with multiple magnetic sensors. I'm Maximilian, and it's my pleasure to present this work, which is a collaboration with multiple of my colleagues at the Cognitive Robotics Department of the Delft University of Technology. The high deformability of soft robots makes it very challenging to control them, but at the same time also renders them a promising candidate for close collaboration with humans, as you see it here in the video on the right side. The state of the art is to use a model-based controller consisting of a feed-forward and a feedback term, but really don't matter what controller you use. Usually you need some kind of state feedback consisting of the current configuration of the robot and the time derivative of the configuration q dot. There has been quite a lot of work in the field and a lot of variety of different sensor modalities on how to sense a soft robot's shape. So some works have attached cameras, for example, to the tip of the soft robot and are running SLAM. Others are using piezoresistive strain sensors integrated into a skin on the outside of the soft robot. However, another very interesting alternative is magnetic sensing, because magnetic sensors are compact, highly sensitive, and can be very easily integrated into soft robot designs. They usually measure the magnetic flux density and output a voltage you can extract. With that, they can provide fully proprioceptive measurements at the cost of just a minimal decrease in softness. However, actually interpreting these measurements is quite challenging because the magnetic fields are highly nonlinear, and we only know of analytical closed-form solutions for highly simplified geometries and arrangements. There has also been some work in literature on how to integrate magnetic sensing into continuum soft robots. Here you can see some examples of that. We note that all of these examples are either looking at a 1D or a 2D case. And all of them also assume the magnets and the magnetic sensors to be positioned or placed in coaxial pairs. This hugely limits of what we can do and which kind of deformations we can measure. And we want to bridge this gap in our work. So we also integrate ring magnets into our robot. They are placed along the center line or the backbone of the soft robot. And then we allow the placement of multiple magnetic sensors at really various points along the soft robot. So we have no requirement for them to be placed in coaxial pairs. And we extract and read out the sensor measurements. We have developed a prototype where we have integrated this methodology into a pneumatic soft segment consisting of 3 air cavities. The cylindrical magnet is embedded into the center of the soft robot, and we have on top or on tip of the robot we have a PCB with 3 magnetoresistive sensors. Really, one key component of our methodology is the access to a kinematic model. So somehow we need to be able to transition from one point of the soft robot to another point as a function of the current shape or configuration of the soft robot. So essentially we need to access to SU3 transformation as a function of the current configuration Q. So for example, this allows us to transition from the base of the segment to the magnet, or from the base to a sensor, and so on. The most popular kinematic parametrization in literature is piecewise constant curvature, also abbreviated with PCC, which assumes the curvature to be constant along each segment. But our method is really agnostic to the chosen kinematic parametrization. So in some of our simulations, we have, for example, also used piecewise affine curvature which uses a linear function with respect to a point coordinate S to model the curvature. So we start off with some kind of initial configuration estimate Q hat, and we send this through our magnet sensor kinematics. So if we zoom into our magnet sensor kinematics, we can see that this really describes the spatial relationship between each magnet and each sensors using just a couple of variables. So here we have, for example, the distance between the magnet and the sensor, the angle in orientation, the angle of the sensor measurement direction with respect to the Earth's magnetic field direction, and so on. And our hypothesis is that this set of variables is sufficient to estimate or reconstruct fully the magnetic field at the position and orientation of the sensor. So when we want to train our model, we still have obviously the ring magnet and magnetic sensors integrated, but now we also add motion capture markers to have some kind of ground truth pose information about our soft robot. We run inverse kinematics on these motion capture markers. We send these poses, or we rather use the configuration to get this magnet sensor kinematics between each magnet and each sensor. And now we use this kinematic parametrization as an input into our neural network. And the neural network tries to predict sensor measurements. So it tries to predict what these sensors are actually measuring. And obviously at the beginning, there will be a mismatch, and we can formulate an error term, and we can optimize that using gradient descent. So we continuously or iteratively update the weights of the neural networks such that our predicted sensor measurement match as accurately as possible the actual sensor measurements. Now, after we have trained our neural network, we move on to actually using the structure doing online optimization. So again, we start with an initial belief of the configuration. We send it through our magnet sensor kinematics, the trained neural network, and we have some predicted sensor measurements. We compare it with the actual sensor measurements. There will be a mismatch now, not mainly because of the neural network, but actually mainly because our belief of the configuration is wrong. And we can leverage that for optimization. So we iteratively update now the configuration Q hat such that our predicted sensor measurement match the real sensor measurement as accurately as possible. And what we end up with is an estimated kinematic configuration. So a kinematic configuration describing the shape of the soft robot. A nice property about our methodology is that this whole loop here is differentiable using some kind of autograph mechanism, for example, using PyTorch autograph. And with that, we can perform efficient gradient descent for this optimization. Here we have an example of how this gradient descent looks like on a set of experimental data. So this is just one instance in time. And here on the x-axis, we have the one configuration variable. So this is the bending around the x-axis. And on the y-axis, we have the bending around the y-axis of this robot. With the colors, we signify the loss, which is namely the error between the predicted and the actual sensor measurements. And we also here we point out the current and the initial configuration estimate. The ground truth configuration estimate is denoted with this green square. And we can see how gradient descent goes down along this loss landscape towards the local minimum. Obviously, there will be a small mismatch between the local minimum and the ground truth configuration, as our neural network will never be trained perfectly. You also can see how here this robot on the right, how the shape from the initialization slowly goes towards the ground truth state. Then we moved on to some simulations where we simulated a robot or the magnetic field of a robot with multiple sensors and magnets attached to it. In this case, we modeled the robot to behave according to affine curvature. And with the slide transparency, you can see the estimated shape of the robot, and with the solid ones, you can see the actual ground truth shape. Again, same here on the right side. So with the dashed lines, you can see the estimate, and with the solid lines, the ground truth configuration. And you can see that we are able to reconstruct or predict both the sensor measurements as well as then optimizing over the configuration. Then we move on to some actual experimental verification on a PCC segment. So again, with the dashed lines, we have the estimate, and with the solid lines, the ground truth. And we can see here that our robot or that our methodology actually perfectly reconstructs the shape of this soft segment. So in conclusion, we have proposed a shape sensing strategy for soft-bodied robots relying on multiple embedded magnetic sensors. The decoupling of the kinematics from the learned sensor measurement predictor allows us to modify the placement of the sensors without having to retrain the neural network. And a nice property is that we are agnostic to the use kinematic state parametrization. We have verified it in extensive multi-segment simulation using both PCC and affine curvature models. And we also have conducted preliminary experiments on a one-segment robot model with PCC. For future work, we would like to verify or validate the proposed methodology to execute closed-loop control. So to use the estimated configuration to then as an input into our controller. And we also find it very interesting to investigate the optimal placement of the magnetic sensors in the continuum soft robots. So as you remember, we have just placed always these sensors on the tip of each segment, but this is quite arbitrary. So you could imagine that there's some smarter ways to do this placement of the sensors. And a nice tool for this would be, again, to use gradient-based optimization to move the sensors around. Thanks a lot for your attention, and we would like to invite you to have a look at our paper, which was published in Soft Matter, and also run our code, which is published on GitHub. Thanks a lot for your